Hello, good people. Welcome to video number three. Before I go on, I do want to make a correction. Back in, I believe it was video number one, we had talked about finding the slope values at each x coordinate and then plotting the green points as the slope values, and the green points were going to create f prime, right? So all these green points, if I connected them at some point and I made it maybe create it more, I would get f prime. I do want to make a correction. F prime of 1, the slope at x equals 1, we said the slope was negative 1/3, and we wrote it down correctly. But when I plotted it as a positive 1/3, and that really should be down here, right? So just wanted to make that correction before we went on, in case you caught it the first time and you were saying, "Wait a minute, is he okay?" Because that's not correct. You were correct if you caught it. I just caught it right now. So here we go. In the last video, we were creating derivative graphs based off of polynomial functions, but in this video, we look at more complex graphs, I guess. What happens when we don't deal with polynomial functions? Then we're going to have to go looking for very specific things, like um, what happens if there aren't any horizontal tangents and I can't find those x-intercepts of the derivative? What if I can't find vertical or horizontal asymptotes? What if the point doesn't at the point that we're looking at, the derivative doesn't exist? What if we have discontinuous functions or piecewise functions, right? And so it's helpful to sketch a few tangent lines to kind of get the idea of what the slope is at specific points. We can do that. Remember that if a function is not continuous, or if it has a sharp turn, or if it has a cusp, then that point is not differentiable. And if it's not differentiable, it's because the derivative doesn't exist. That means there's not going to be any point on the derivative graph at that x value. Also, if f of x is not differentiable, then f prime does not exist at the point. That's what I just said. This means that there won't be a point. There will not be a point on the graph of f prime. So this could come into play as a hole in the graph or a jump or a vertical asymptote. So non-differentiability in the original function means some kind of discontinuity in the derivative function. So let's start with something like this. Can we figure out the graph of h prime? And so let's look for some significant things that should stand out. I notice that at these points, and I'm going to highlight them. Let's say this one and this one and this one and this one. What do I know about the slopes at those blue points? Well, I know that the slope is 0, right? I have horizontal graph, so the slope is 0. So that means I can put here and here and here and here. So in green, I'm going to create the graph of the derivative. So h prime will be in green. But in between those blue points, that's also a flat part. So that means the slope is also 0. And if I go to the left, all the way up to 4, the slope is 0 because I have a constant part of the graph. But when I get to 4, this, my good people, is a non-differentiable point, right? We have a sharp turn in the graph, so the derivative doesn't exist. So at this point, h prime doesn't exist. So therefore, when I go to the graph, I should have an open circle because there's no derivative value at x equals 4. Now, to be clear, the derivative exists to the right of 4, and the derivative exists to the left of 4, right? All of these slopes are positive. And then after this sharp turn, all of these slopes are 0. But at that one corner point on the graph, the derivative doesn't exist. So that's why I have to create that open circle, because I don't know what's happening there. Now, if I keep going to the right side over here, same thing over here. Hey, my slope is 0 all the way to 7, but then at 7, there's a jump discontinuity. So if it's discontinuous, it's not differentiable. And if it's not differentiable, the derivative doesn't exist. So I should have an open circle there. In between 7 and 8, I have a constant function, so it's flat. The derivative is 0. the derivative is 0. The derivative is 0 all the way until I get to 10. And at 10, because I don't know what happens on the other side, I can say that the derivative doesn't exist there. I can't put a tangent line at a point where I don't have another side of the point. It's just the graph ends there, so that's that. So I should have a flat graph, a horizontal graph, a constant graph at 0, except at these 3 points because something weird, quote unquote, is happening. Okay, so let's go back now to x's that are less than 4. What's happening over here? Well, I noticed that my slopes start out pretty small, like close to 0, and then they get bigger and bigger and bigger and bigger. As a matter of fact, right here, and I'm going to draw it in purple here so that you can see, this is not the tangent line. Maybe I should try to do just... This is not the tangent line, but that's a pretty good approximation for the tangent line at this curve, and that is 1/2. So that means the slope in this part could be around 1/2. So that means my green dot should be here. Now after that, my slope gets bigger and kind of like here, I guess. My slope is kind of like 1. So somewhere here, the slope is 1. I don't know, maybe here. I'll just split the difference. And then it keeps getting bigger, but it's not like growing to infinity. So when I finally get to this part, the slope somewhere here was maybe close to 1, and maybe it's a little bit more than 1. I don't know. By the time I get to here, I'm going to say that my slope is somewhere here. And let me do this here. So my slope here is a little bit more than 1, something there. But then everything over here, my slope is getting smaller and smaller and smaller as I go this way. So I should have like a curve that goes up to there. This is the graph of H prime. Why? Because my slopes on the original graph are positive but really close to 0. Look at the graph, the green graph. It's positive above the x-axis and pretty close to 0. But as I move to the right, my slopes keep getting bigger and bigger and bigger. And in this part, my slope is 1/2. So my graph should be getting bigger and bigger and bigger. And in this part, it reaches 1/2. And then the slopes increase. They get to 1, maybe a little bit more than 1. And so as I go here, my green graph goes towards 1, and then maybe a little bit more than 1. And this could be the graph of H prime. Is it exactly? Well, no, it's not. We don't know, right? Because we can't, unless we zoom in and try to find a lot of tangent lines, we can make a better graph. But this is a sketch of what H prime could look like. Let's try another one. Whoa, what is going on here? I don't know. Let's find out. What do we know about this graph? We know that the slopes are always positive, right? As a matter of fact, right here, the slope is almost vertical. So if it's almost vertical, that means it's an infinite slope because it's straight up and down. And so what we're going to say is that the graph of f prime is going to start way up here because this slope is really, really big. Now what happens? Well, the slopes get less and they're still positive, but notice they're kind of leveling off. The slopes are becoming almost horizontal by the time I get to 12 over here. Okay, so if my slopes in purple are leveling off, they start really, really steep and positive, and they become less positive, less positive, less positive, going towards 0. Then my derivative graph is going to start really, really positive, and it's going to get less positive, less positive, less positive, and it's going to approach 0. This could be the graph of f prime of x. Why? Because the behavior of the slopes that I represent in purple here of the original graph are the y values on this green graph. So if my slope is really positive, then my green graph is really positive, the y coordinate, right? If the slope is less positive, my green graph is less positive. And if my slopes are approaching zero, well, then my green graph is approaching zero. The y coordinates, the y values on the green graph represent the slopes on this original curve. Maybe it is. Maybe it is. I don't know. Maybe it's shifted a little bit to the left. Maybe it's just shifted a little bit to the right. But the idea is that it has this behavior as it's getting closer and closer to the x-axis as x goes to infinity. Okay, let's practice again. The more we do these, the easier, more comfortable you become at it. Anything stand out? Yes. There are some places where I have a slope of zero, right? Slope of zero here and here and here. And really anything here. All these are slope zero. Except when I get to the endpoint, well then there is no slope there, because how can I balance the tangent line at one point when I don't have another side, right? So it doesn't really exist. Same thing on this one. Hey, it doesn't exist because I have a non-differentiable point. I have a sharp turn, so the slope doesn't exist at 3. But it does exist before 3. This slope looks like it's 1, 2, 3 up, 1, 2 over. So that's 3 over 2, or 1.5. So this slope is 1.5. So at x equals 2, the slope is 1.5. But it's also 1.5 this way, all the way until it gets to 3, and then it doesn't exist. And then it's 1.5 this way, all the way until it gets to 1, and then it doesn't exist. What happens at 1? Well, it's a sharp turn, and sharp turns have no slope, right? The slope doesn't exist. So therefore, the derivative doesn't exist. But the derivative, the slope, does exist to the left of 1. I notice that all of these slopes are -1. It goes down 1 over 1, down 1 over 1, down 1 over 1. So my slope in this section should be -1. So I'm going to draw, and because it's always -1, I'm going to draw a horizontal line from -4, which should be open, all the way to 1, which should also be open because the derivative doesn't exist. Now, if you think about it, if you look at, so this is the graph of K prime. If you think about it, look at the graph. The graph has 3 line segments. That means there's 3 places or 3 sections where the slope is constant. The slope is the same here from between -4 and 1. Hey, the derivatives are the same here. All the y values of the derivatives are the same here. The slope is the same here from 1 to 3. Hey, my y values of the derivative are the same here. And the y value is 1.5. That's the slope in this section, in this interval. And then after 3, my slope is 0. Hey, the y values of the derivative graph are 0. The y values of K prime represent the slopes of K. Let's try one more, and we're going to make it a doozy here. Let's think about what's going on with the graph before we start plotting anything. So I'm looking at the graph. This is the graph of G. I'm looking at the graph. The graph has pretty horizontal slope, so almost 0 slope. But then it gets more negative, more negative, more negative, more negative, more negative, really negative, right? I'm not talking about the y values because the y values are all negative. The y values of G are all negative. I'll talk about the slope. And so when I look at the slope, when I draw these tangent lines, they get more and more negative. So the graph could look like this. Close to 0, and then more negative, more negative, more negative, more negative, more negative, and then it just goes down to infinity. Now, if it's going down to infinity, that means there's a vertical asymptote. So there's a vertical asymptote for, I didn't mean to draw that color, I apologize. There's a vertical asymptote for the original function, but it looks like there's going to be a vertical asymptote for the derivative because the derivative has infinite behavior. Okay, what's happening on the other side? Well, as soon as you flip over the original asymptote, this is really negative slope. and then it's less negative, and then it's less negative, and then less negative, getting closer to zero, less negative. I'm supposed to be drawing these tangent lines, and the slopes of these tangent lines are getting closer to zero. So if you think about it, we started really negative, and then we go less negative, getting closer to zero, less negative, less negative, less negative, and we're getting closer to zero. And so we get something that looks like that. Is it exact? No. But this is the general shape of g prime of x. The green graph, which represents the derivative, is plotting, as the y values of the green graph, it's plotting the slopes of the original function. In the next video, we'll talk about 5.9 and how we can connect the idea of the original graph with its derivative graph with its second derivative graph. And we'll get a chance to practice this in class as well.